Welcome back to 7.4. What we've done so far is learned about the component form, the IJ form, and how to find the magnitude and the direction angle and how to use those as well. And so everything is kind of at the core level. You'll want to do as much homework as you can. So don't skip the recommended homework. That would be detrimental. You want to just get really proficient at this. So what they have is a couple of applications, and these two applications are going to be pretty insightful. And then they move on to a dot product, which helps us satisfy some other requirements as well. So getting organized here. As we go to this one, two forces of 37.8 and 53.7 pounds act at a point in the plane. The angle between the two forces is 68.5 degrees. Find the magnitude of the resultant force. This is where the parallelogram rule will really help. So as we focus on this particular problem, let's draw it. So you're going to draw two forces, and just trying to draw it as best as I can. This is 37.8, and this force right here is 53.7. So if you remember, we used that word resultant before. That was then the addition of the two. So the best way to handle this problem is to use the parallelogram rule. And I don't like how I've drawn these, so I'm going to take a step back. That doesn't look like 60 degrees. It looks more like 90, which might be upsetting to some. I don't know how best to say that. So let me make that angle between them more like a 60-degree angle. Now, as I do that, I'm recognizing that I need to drop lower. So I'm going to redraw the 37.8. And I'm going to redraw at what I feel is more of a 60 level. Okay, this guy right here. Okay, the 53.7. And so I'm going to come in here, and in my red dotted, I'm going to try to stay parallel to the 53.7. And then we're going to do the 37.8 line. And so it's absolutely not perfect, but it gets their general feeling. So remember, this is still 37.8, and this is 53.7 because you're drawing a parallelogram. What they're asking you to find, I'll put in blue, they're asking you to identify the magnitude of the resultant force. So they want the length of that line. So they want the magnitude, let's call this, for lack of a better way, u. They want the magnitude of this vector u. That's the resultant force, the force that has the two powers combined. Well, how are we going to do that? Well, we do know a few things. We know that this is 68.5, right? The angle between the two vectors is 68.5. If that's true, then this is a parallelogram. I don't know if you know this property, but the two adjacent angles in a parallelogram need to be adding up to be 180. So this one right here, I'll put in, I don't know what color will stand out as much as I need it to. I'll put in red. We know that this angle right here is 111.5, right? Am I thinking about that right? 180 degrees minus the 68.5. Yeah, 111.5. Okay, so 111.5. Now, why is that needed? Well, let's take a look at just that triangle. In this triangle, we have this red top. We have this black side, right, just so you can see which ones we're looking at. And we have this blue diagonal that we want to find the length of. So if I just break that triangle out and put in what we know that's important, we know an angle in there, and only one, 111.5. That blue line's definitely not cutting 68.5 directly in half. The only way it would is if that was a 90-degree angle, but it's not, right? It's a 68.5. So we know that's 111.5 in there. We know this is 53.7. we know this side right here is 37.8, and we are looking for this blue side. So guess what you use? Well, you either use the law of sines or the law of cosines. If I try to use the law of sines, I got a problem because I don't know any angle opposite a known side, so it must be the law of cosines. So what do? We remember that the side that we want squared is equal to the sum of the other two sides. And you can start to see why trig is going to be so important. Because if you think you're going to go into engineering or something like that and not have to deal with forces, uh, you're missing a major component of that class, right? And so a lot of it's going to come down to trig. And remember, it's minus. I had put a plus. Minus the product of the two, 37.8. And I didn't start out far enough. I apologize for that. Let me go over here. So the magnitude of u squared. Oh, okay. Our book, apologize. Most books that I grew up with did a double line, so people didn't mistake it for an absolute value. This book uses only a single line. So I'm just going to copy this really quick, because what you'll see is that I'm running out of room because I need to get a cosine in there as well. And then times the cosine of that known angle, 111.5 degrees. And when you run all of that, you'll find that the magnitude of u is simply equal to 76.2. Okay, so I pre-ran it just for the sake of time, but 76.2 is the answer to this one. So the resultant force magnitude is 76.2. So if you're putting a 37.8 pound and a 53.7 pound and they're acting at the same point in a plane, the resultant is a 76.2 pound force. And if they needed to know the direction, we could figure out the direction that that force would be coming in at. And sometimes you do need to know that. Right now they just want us to be concerned with the magnitude. So you can see why they put this section right after 7, 1, 2, and 3, because that's where we learn the law of sines and law of cosines. So if we go to this next one, it's going to be the same thing, except they've drawn it out for us. So what do we need to do? We need to come in here with our red lines and try to create the parallelogram that we need. Okay, and then this is going to come in like this guy right here. So I didn't need that extra stuff out there. Let's see if it will just erase those bumps. Okay, so what are we looking for? It's the exact same problem. We are looking for this blue line right here. What do we know? Well, if this is 140, we know that this top angle is 40, because remember, they have to add up to be 180. Okay, so that top guy there is 40. So remember, this is 1500, this is 2000, so we're set. We need to find the magnitude of that blue line. So let me go in blue. The magnitude of u is equal to u squared, right? If I call that u again, is equal to the 1500 squared plus the 2000 squared minus 2 times 1500 times 2000 times the cosine of 40 degrees. And when you run all of that and do your square root, you'll find your magnitude of u is equal to 128.6 pounds. Right? So even though you're applying a massive amount of force, because of the angles in which they're being applied at, the resultant vector is not as strong as a force. That blue line is way shorter than those other lines. And we're finding out that it's 120, oh, I apologize, I misread my writing, 1,286 pounds. 1,286 pounds. There's no decimal point in between there. I actually looked back because it seemed like that's a way smaller line, right? That u does not look drastically different than the 1500 line, but if it was 128.6 it would have been, but it should be 1,286. Awesome. So that's what you're doing there, a nice application of vector addition, which we learned in the beginning just through the parallelogram method, and using previous skills to come up with the length of a line. It's a lot of what math is as you move forward. And then the last example, notice this is number 66. So they're going to stay to the core. These were in the 50s. They may seem harder because we had to rely upon something from before. But these are going to be like the ones that we did towards the beginning. 2u plus v minus 6v. Well, let's get 2u. 2u is going to be doubling the u, so a negative 4 comma 10. Now we need to add v. v is 4, 3. And now we need to subtract 6v. And 6v is 24 and 18. So what do we have to do? Just add up our x components. And those add up to be negative 24 because the two 4's cancel out. And we got a minus going into the 24. 10, 13 minus 18 is a nice negative 5. And we're finished. Doing nothing more than combining like terms. So now we're going to get into something called the dot product, which is still here in 7.4, and it has an application that they'll want us to use. The dot product is a number. It's not another vector. So it's done in a way that gives us this number, and the number is very useful in a couple of instances that I can think about. One main one that they'll point out here. And so the dot product is defined in that upper blue box. It is simply just the x components being multiplied, the y components being multiplied, and adding those results. Because of that, the dot product is commutative, it's associative, it's distributive, handles numbers well. It's not a problem. Everything is great. And so this dot product is very nice. The biggest thing is that you're getting a number, not a vector, right? So that's that big note right there. You're getting a number, not a vector. So that's why they call it the scalar product. So the geometric interpretation of the dot product is that it helps us get the angle between two vectors. And that's a really important thing, to know the angle between two vectors. And so they use the cosine. That's because they always define the angle between two vectors to be the smallest angle. So if I had a vector here and a vector here, the angle between them would be this theta. They'll never consider this. They'll always pick the smaller distance. So if they start to look like this, then it's this angle. Right? Always the smaller of the two. So it's bound between 0 and 180, and that's why they're using cosine. Because when you do the cosine inverse, it will give you only angles between 0 and 180 degrees. So it's awesome. So let's just practice finding the dot product, and then we'll find the angle between some vectors as well. You'll recognize that this work is not bad either. So 7, negative 2, 4, 14. What's the dot product? The dot product is 7 times 4 plus negative 2 times 14. So 7 times 4 is 28 minus 28. And so the dot product is 0. Now 0 is not a bad dot product. In fact, you like it when it happens. 0 tells us something. Remember that the angle between these two vectors is equal to the cosine of theta. Cosine of that angle is equal to the dot product, which you just found out is 0, over the magnitude, which is, I don't care, because they both have magnitude, but I don't care what they are, because what's 0 divided by anything? Well, it's 0. Tell me, cosine of theta equals 0. What angle would that be between 0 and 180? Obviously 90 degrees. 90 degrees means that these two things meet at a right angle, and that they're what they call orthogonal. Orthogonal vectors have 90 degrees between them. Their dot product is 0. So you wouldn't even need to use the formula. As soon as you recognize a dot product is 0, you know those two vectors are nailing each other right at 90 degrees, right? Or coming together at a 90-degree angle, or 90 degrees apart from one another. Now, they didn't ask any of that. They just wanted to know the dot product. And so the work that I'm leaving is the answer to the question. How about this one? The dot product of 2i plus 4j, and then another vector, negative j. So what do we have? So they chose to do this in the ij format. So I would have the I component of one times the I component of the other, which is nothing, plus the I component of the first times the the j component of the first times the j component of the second. And so what do we get out of this? Very quickly, a negative 4. So now let's put this all together. Let's find the angle between 1.17 and 1,1. Easy. We remember that cosine theta is equal to u dot v all over the magnitude of u. Sorry, I'm using my old notation. All over the magnitude of u times the magnitude of v. So we got to find a lot of things. First thing we need to find is, I'm going to call this u and v. We need to find the dot product of uv. Not bad. UV's dot product is 1 times 1 plus 7 times 1, or 8. So we're getting a nice dot product of 8 out of there. Now we need to get the magnitude of u. The magnitude of u is 1 squared plus 7 squared, which is equal to the square root of 50, which is equal to 5 root 2. And the magnitude of v is equal to the square root of 1 squared plus 1 squared, which is the square root of 2. So, not bad. We have all of that working for us to help us out. So, individually, easy steps. So now let's come back up to the top. What's u dot v? Well, that's 8. What's the magnitude of u? 5 root 2. What's the magnitude of v? Root 2. Let's simplify that. That's 8 over root 2 times root 2 is 2 times 5 is 10. So that's 4/5. So what we need to do is take the cosine inverse of 4/5. Okay. And again, I'm sorry for my hand hitting that. But here's where we were. So let's take the cosine inverse of 4/5, because that's what theta is going to equal. Cosine theta is equal to 4/5. Cosine inverse of 4/5, I'm not sure why I did that, is equal to theta. Right? That's why we did the solving of equations first as well. So let's go find that. What's cosine inverse of 0.8 or 4/5? And we get a nice 36.869 degrees. So maybe we'd say 36.87 degrees is equal to theta. You put 36.9, no problem. Right? 37, probably still give you full credit because I can see your work, right? That's the angle between the two vectors. They're often not super nice. Now, determine whether each pair of vectors is orthogonal. It's only orthogonal if cosine theta is equal to 0. Well, the only way cosine theta is going to be equal to 0 is if u dot v is equal to 0. Right? Because you're never going to get, your magnitude is always going to be something positive. Never going to be 0 down there. So the only way you can get 0 is if u dot v is equal to 0. So let's look at this first one. 1 times 1 plus 1 times negative 1. Are they orthogonal? Yes. 3 times 6 plus 4 times 8. Are they orthogonal? Absolutely not. You don't even need to figure that out. I mean, you could, but why? You know that's not going to be 0. How about this one? Negative 4 times 8 plus 3 times negative 6. Those are both going to be negative and have big numbers. That's not going to go to 0. That's a no. And so we're done just that quickly because we're looking for zeros in that process. So that is what we're looking at to finish out the 7.4 section, is just this idea of dot products and how they can really help us out. So try the 7.4 homework. Let me know what questions or concerns arise.